Hello and welcome. Today is Wednesday, April 15th. Uh, Today we'll take a little bit of notes on combination circuits. We'll combine a few of our series principles with our parallel principles. We'll see that circuits don't have to be just series, just parallel. They could be both or neither. And today we'll see how they can be both at the same time. This is similar to how rivers can break apart into smaller channels like little blood vessels and capillaries, and then eventually they recombine again as it goes back into the heart. Is anyone here? Well, you're here, so that's all that matters, right? Good job, Chris. Dennis is also here. I'm sure people will wake up. All right. If you looked on the second page of your calendar, you'll see this picture here, and this picture shows you what we're going to talk about today. Here at the top left, you have a battery. The battery sends the current out. We have a resistor here of 2 ohms, and then there's like a fork in the road, and it splits up into 2 pathways. Some of the current will go through the 3 ohm resistor that we have here. Some of the current will go through the 6 ohm resistor that we have here. And then eventually the 2 individual streams will recombine and go back to the bottom of the battery. Right? And so what we could do is model this using gravity. The battery, which is in this case 10 volts, will boost you up, kind of like an elevator. You're going up 10 volts, and now you're on the 10th volt floor. And as you go across a resistor, you're actually taking the slides or steps downwards. So when you go through the 2 ohm resistor here, you fall in a certain amount, and then whatever is left, okay, gets split up. You can take either pathways. Both pathways will lead you to the same spot, to the same destination. Right? It's just a different journey, a scenic route. So some of them will go through the first resistor here, and the rest will go through the other one. Eventually the 2 streams will meet up, and now you're at 0 volts on the 0th floor, and then you'll return back to the elevator, so you can take this amusement park ride all over again. So that's how it works. And this picture also kind of breaks down and simplifies the circuit, breaks down the voltage drops, etc., etc., and we'll talk about that today, right? We can also do a few mastering physics problems later on after we go through the combination circuits. We did all the way up to 12. We're pretty much doing the whole homework assignment at this point. That's all right. So today we'll do 13, 14, 15, 16. Alright, so let's begin by drawing this circuit out. Pull up. Alright. No, there we go. So we want to draw this circuit. So combo circuits, starting with our battery. Remember, it's a big line, small line, and the big line is the positive terminal. Okay, so we have a resistor here, and then we split. I'm going to draw it slightly different so that it looks nicer. We'll draw the fork kind of like a Y fork. This will force your brains to process the flow as it splits up and recombines. There we go. Okay, if I draw the current flow diagram, of course it comes out of the plus end, positive, goes through here. We get to a junction here, and once we get there, we split up. Some of it will go through the first route. The rest, whatever's left over, will go through the other route. Oh, I don't want to use this color. Let's use orange. And these two will meet up and converge. Right? So I use the analogy of like blood vessels, little capillaries here, but eventually the capillaries converge again and then leads back to the heart. And then the heart will pump it out all over again. It does this over and over, it seems. Okay. Now, when you have complex circuits that have both series and parallel parts, both elements of series and parallel. Okay, we want to identify the resistors that are series and the resistors that are parallel, so that we can start combining them and simplifying them. Similar to how we simplify fractions, we can reduce a circuit down to its simple state, or the combined state, right? It's like finding REQ. So let's give some values. I'll draw it one more time, this time without this current flow diagram. We'll call this 10 volts, 10 volt battery, right? The first resistor, will make it 2. Oh, oops. This is 2 ohms. The second one will be 3 ohms. And then this one here would be 6 ohms. Okay, so here are some values. Right, so the first thing you do is identify which resistors are in series and which resistors are in parallel. Sometimes, it's easy to find one versus the other. So this is going to change and depend on the circuit itself. Okay, so what you want to look for are either junctions, or for series circuit resistors, you want to see if the pathways are closed. Okay, and we'll take a look at both models in a moment. So in this circuit, you can see how there is a junction here, there's a junction here, and when the current comes in and splits up into 2 parts, after going through each resistor, when the first stream goes through the 3 ohm and the second stream goes through the 6 ohm, okay, notice how there are no other resistors that they go through before meeting up, before joining up. So when these 2 streams split and recombine again, that is the definition that we have for parallel. It is based on the splitting of this current. And so the fact that they split and then recombine again means that these 2 resistors are parallel. which means I can replace them. Right? So let's redraw the battery, 10 volts. We will have our 2 ohm resistor, like so. And now I'm going to replace these 2 resistors with just a single resistor that has the combined value of 3 and 6. Now we don't add them. What do? Chat, what is the combined value of 3 and 6 in parallel? Okay. If we label this R1, R2, R3, so what we're doing is combining R2 and R3. So what is R23 equal to? Do you guys still have a delay? I don't know. I thought the delay is a lot less now, isn't it? Let me check. Yeah, it seems... okay. Chat, what is the parallel of 3 and 6? Parallel of 3 and 6. Chapito is here and Nausicaa is here. Oh, we do have viewers. I mean, people have come in. Some of them are lurking, meaning they haven't logged in, so I can't see their names, but they're here. Well, for parallel resistors, we use the parallel rule, which is to do the inverse of the sum of the inverses. So, or you can do product over sum. Product over sum, meaning 3 times 6 over 3 plus 6, so that also does it. So that's 18 over 9, and that's 2. So this would be 2/6 plus 1/6, which is 3/6, and 1 over 3/6 is 6 over 3, which is 2. Alright, so what does this 2 mean? Well, it means that I can replace the 3 and the 6, because they're parallel, I can replace it with another 2 ohm resistor, and that would kind of accomplish the same thing. It would apply the same amount of resistance as having 2 resistors in parallel. Notice how the total resistance of 3 and 6 is actually less than the smaller resistor. So anytime you have parallel resistors and you're doing the total resistance, you'll see that the total is always less than the smallest one. So in this case, the smallest one was 3, and the total is actually less than 3. Anytime you open up a new pathway for charges to flow, you're actually reducing the total resistance in the system. Alright, and then we can look at this new circuit. So we went from this one to this one, and in this new model, current comes in, or comes out, sorry, goes through the 2 ohm, and now it looks like that same current is going through this new 2 ohm resistor, right? Since the same current is going through, we could say that these two are now in series. Okay, there's no fork in the road anymore, so these two are now in series. Therefore, we can combine these 2 resistors into one. So let's go do that. This means that I still have my battery. The battery's still 10 volts. Okay. Instead of using two 2-ohm resistors, we can do the same thing by using just a single resistor that has a value of 2 plus 2, which is 4 ohms. This time we're adding them because the resistors are in series. The resistors are in series. And for series resistors, you add. Okay. All right. So in essence, what we've done is we found the total resistance of our system, Req. Req, which in this case represents R1, 2, 3, right? It's the combination of the 2 ohm here in the front, the 3 and the 6 in parallel with each other, and when you combine everything, the answer is actually 4 ohms. The total resistance in the system is 4. If the total is 4, that means the total current in the system must be equal to the total voltage over this total resistance, and that's 10 volts divided by 4 ohms, which is 2.5 amps. I'm skipping over sig figs for the day. We'll do sig figs some other time, or just change all your numbers to have at least 2 sig figs. So 2.5 amps in our system. So 2.5 comes out of the system, out of the gate here. So if I go back to the original drawing, so this is 10 volts, right? So that means right here at the front, the total current, which is coming out of the battery, is 2.5 amps. Okay, so let's follow this current. So this 2.5 amp comes out, goes through this channel here, keeps on going. Okay, now the first encounter is resistor number 1, and since there are no other pathways for this current to, okay, all of that 2.51 must be going through resistor 1. So we could say that the current that goes through resistor 1, I1, is equal to the total current in our system, I total, which is 2.5 amps. All right. So by using the current flow diagram, we're going to solve for all of our values. So let's go and see if we can make a quick chart. R1, R2, R3, I1, I2, I3, and then we'll also do V2, V1, V2, V3. Okay, of course R1 is 2 ohms. R2 was 3 ohms. R3 is 6 ohms. Okay, we found out that the current in the first in resistor number 1, I shouldn't say first. There is really no first or second in a circuit. All of them get the current at the same time because of it's a domino effect as the charges push one another forward. I1 is the total current, and the total current was 2.5 amps. Okay. Question: does resistor 2 get 2.5 amps? Ooh, let's do a poll. Oops. Does resistor 2 get 2.5 amps as well is the question. Okay, vote yes or no. So I2 is I2 equal to 2.5A. So exclamation point, vote yes for yes, and then vote no for no. No, that's not how you do it. Here, let me show you how to do it. So as you can see, it says a poll has been opened, right? It says exclamation point, and then you have to type the word vote, and then a space, and then after the space you type yes or no based on what you want to do. Right? Shapito, try again. So type exclamation point and then vote, and then your answer. Oh, it's a tough crowd today. There you go. That's how you vote. Good job, Angela. So the question was, is I2 equal to 2.5 as well? So if you did exclamation point vote no, this is what the no would look like. If I go back, yeah, I can actually show you the current live results. So this is, so as you can see, people are voting, and then, man, so this is what it looks like on my screen. Oh no. Whoa, look. Alright, anyway, I was supposed to hit end poll, and then I hit end stream. Darn it. The answer is no. The answer is no. Notice how the reason why I1 was 2.5 was because the stream, whatever stream of water was going through our system at the start, had to flush itself through resistor 1. But after you go through resistor 1, here at this junction, the current splits up into two parts. So these two parts cannot be equal to the whole, right? So these two parts have to be smaller than the whole. They're fractions, you know? And the fractions will depend on the path of least resistance. Current tries to take the path of least resistance. So the path that has less resistance, the 3 ohms, will get more of the current. And the path that has more resistance, the 6 ohm, will get less current. However, the total current that is split up is still equal to the sum, the total, because you can't get more than what you started with. Whatever current goes into a junction, right? So this pink arrow, which represents 2.5, that is going into the junction, must equal what comes out of a junction. So the blue arrow plus the orange arrow must equal the pink arrow. Right? Are you guys still here? I accidentally hit end stream, and now I have to recombine two different streams. This is going to be more work. Yikes. So how do we do this? Well, how do we figure out how much current goes through each pathway? One thing to do this is almost like a puzzle, and we'll do this type of problem more and more, but is to work backwards, meaning since I already have R1 and I1, I can actually find V1, right? Chat, what is V1 equal to? Those of you who are still vibing. What is V1 equal to? If you know what R1 is and I1, we can use Ohm's Law. And Ohm's Law tells you that V is equal to IR. And so V1 must equal I1 times R1. So that's 2.5 times 2, and so that's 5 volts. Oops, not 50. 5 volts. I think I'm going to go ahead and make everything 2 sig figs, so that our sig figs are all nice and neat. So these are all 2 sig figs. This is 2 sig figs. This would be 5.0. It's going to make it all 5.0 volts. All right. Very good, Christian Tran. It's 5 volts. So if the first resistor drops 5 volts, so we've after going through this resistor, we're losing 5 volts. Remember, resistor uses up the electrical potential energy. So since you started with 10 and you lost 5, okay, it's like starting with $10 and now you've paid $5 already. You only have $5 left. That means that no matter which pathway you take, no matter which route you take, whether you take the blue route or the orange route, okay, you're going to lose the rest. So you're going to lose 5 volts here, and you will lose 5 volts here. Okay, because you only have 10 total, so you lost 5 already in the first one. Therefore, whether you take resistor 2 or resistor 3 doesn't matter, and you can only take one resistor at a time. You can't take both. So imagine yourself kind of at this amusement park, right? We were talking about at the start of lecture, right? You can only take one of the slides. Either you take the left one or the right one. Whether you take the 3 ohm or the 6 ohm, you can only take one, but by taking either of them, you will lose the rest of your voltage. Well, how do I know you're going to lose the rest and not just a partial? That's because once you get to the bottom of the battery, you're at 0 volts. And so you have to go through it again to get boosted up to 10 volts again. So any point along this line here, all these X's, okay, represent the same nodal point, meaning it has the same electrical potential, 0 volts, because all of this is connected to the bottom side of the battery, which is our low point. All right, so that means that V2 is also equal to 5, and V3 is equal to 5. Now, don't just assume that, oh, V1 has to equal V2 has to equal V3. And remember, this is a complex circuit. It has both elements of series and parallel. It's just sometimes, you'll see some coincidences, but this part is not a coincidence. The part that V2 and V3 have to have the same voltage. Have same voltage since they are parallel. All right. So we know that V2 and V3 have to be the same because 2 and 3 are parallel. Well, why did 1 equal 2 and 3? Well, that just happened this time around just by coincidence, just by the mere fact that the total resistance of the second and third resistors, R2 and 3, we found as 2 ohms, right? It's only because their total was 2. Since their total was 2, they share the same amount of resistance as resistor 1. Only because their total somehow equaled the first one is the reason why the voltages were the same. So if the rec of R23 was different, then V2 and V3 would be equal to each other, but it would be different from V1. And we'll do other problems where it is different. Right? So let's see. Now that we know what the voltage is, we can go backwards and solve for the current. I2 must equal V2 divided by R2. We're just using Ohm's law. Voltage over resistance is current. So that means 5 volts divided by 3 ohms is equal to 5 over 3. What's 5 over 3? That's 1 point. That's like 1 and 2/3, right? 1.6, 1.666, or we'll just say 1.7 because we're using 2 sig figs amps. Okay. All right, so I3 must be V3 over R3, and that's also 5 volts, but this time over 6 ohms. And so 5 over 6, what's 5 over 6? That's 5/6, like 80 something percent, 83%. Five over 6, 83%. So I'll just write 0.83 like this. All right. So as you can see, it splits up. The 2.5 splits up. Now, because of sig figs, they might not, be perfect. It might not be equal. But let's go and add these two. What does I2 plus I3 equal to? So the total here would be 1.7 plus 0.83, which is, of course, if I use more sig figs, we'd get a much more accurate answer. Right? We're getting, if I use 2 sig figs for the answer, we get 2.5. Yay, it works. Oh, we're not, when you add and subtract, remember you're supposed to use the least amount of decimal places. So the least amount of decimal place is 1 decimal place. So it rounds to 2.5, which is perfect, right? You can see how, based on our junction rule, okay, recall that we had blue going out, orange going out, and the pink going in. Pink. Okay, 2.5 went in, and it split up into 1.7, or it's like 1.66666, and 0.833333 amps. All right, so we'll leave that there. Tomorrow we'll do another one, something more complex, or perhaps even I'll take a few questions for Mastering Physics. Remember, we're supposed to do 13, 14, 15, 16 today, so let's start. So that's it for our notes portion. So Mastering Physics 13. Mastering Physics 13 says, pacemakers designed for long-term use commonly employ a lithium iodine battery capable of supplying 1500 coulombs of charge. So pacemaker is like something that you put inside your heart. It sends an electrical signal onto your heart to force it to kind of, force it to beat at a certain frequency. So if you have, various issues, problems, the pacemaker will make your pace your heart. Um, and so you basically get heart surgery, and then you put an implant inside your heart called a pacemaker. Um, Now, it is battery powered. Newer technology uses something called electromagnetic induction or inductive coupling, so we can somehow wirelessly charge the batteries up, so we don't have to cut it out again and replace the battery. Otherwise, you have to get like heart surgery every now and then, which is no bueno. So a pacemaker is supplying 1500 coulombs of charge. All right. If the average current produced by the pacemaker is 5.6 microamps, what is expected lifetime of the device? Okay. So we can use the definition of current. Current, remember, is the amount of charge you have, delta Q, over the time, delta time. So if I want to know how much time, the time must be equal to, if I do the old swapperoonie, remember when you solve for variables, just put a 1 underneath the single variable and then cross multiply the two and solve. So always put a 1 underneath and then cross multiply. So if I cross multiply, I get delta Q divided by the current I. So Q is the charge, and the charge is 1500 coulombs in my version, and current is given as 5.6 microamps, but I need it in standard units and micro. 5.6 microamps is the same as 5.6 times 10 to the negative 6 amps. Okay, and that should do it. So that's the time. Moving on to 14. Mastering Physics 14. In 14, it says a circuit consists of resistors 170 ohms, 240, and 65 connected in series with a 12-volt battery. How much current flows through resistors? Oh, okay. So based on the information, you should be able to draw the circuit out. It says 3 resistors, blah, 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 are in series. Series means they are one after the other. The battery is 12 volts, so let's see. Here's our battery. And then we have 3 resistors, 1, 2, 3, and then we're back to the battery. Make sure you draw one big line and one small line. My values are 170, 240, and 65. And so, of course, to find the current I, we have to do V total. So I total is equal to V total over REQ. And REQ is easy. You just add them up because they're in series. R1 plus R2 plus R3. So it'd be 170 plus 240 plus 65. And once you do that, then you can just divide the voltage, V total, which is 12 volts, divided by the total resistance. Right? The reason why we solve for I total is because this is a series circuit. So whatever current comes out of our battery has to go through all 3 of them because there are no other paths. There's only one path. One path. And when there's only one path, then each individual current must be the same. Must equal, in this case, the total current as well. Okay, the current that goes through the resistor 1, the current that goes through resistor 2, they're all the same. The second part says, what is the voltage across the resistor 170? Now we're looking for individual voltages. Let's call this V1, V2, V3. And so if we're looking for individual voltages, then use individual values. V1 must equal I1 times R1. Now, all the I's are the same, so whatever answer you got for the first part, multiply by the individual resistor. So if you want the voltage for the 170, you'll have to multiply the current you found times the resistance of just R1, not the total. Okay. And of course you'll see that the values drop in pieces. So let's see, what is this total? 170 plus 240, 170 plus 240 plus 65. That gives us 475 ohms. And so if I did 12 divided by 475, 12 divided by 475, that is 0.0. The zeros don't count. 253. That's 3 sig figs. Based on the values, I should use 2. So this is approximately 0.025. Yes. Okay. So once you know that, you can just multiply 0.025 amps times the 170 ohms of resistance to get the individual value. Problem 15. Resistors 88, 130, 270 are connected in parallel. How much current is supplied by the battery? All right, now they're in parallel. So measuring physics 15. So battery, here's our battery. Let's go and draw them in parallel. 1, 2, 3. My values are 88, 130, and 270. They're all ohms. This is still 12 volts of 12 volts from the battery. Same thing. So I want to know how much current is supplied by the battery. So whenever it says by the battery, that means the total. How much current is coming out of here? That's I total. And of course I total will split up into 3 parts, 3 little capillaries. But I total must equal V total over rec. But rec is different. You can't add them up. You have to use the parallel rule. That's 1 over 88 plus 1 over 130 plus 1 over 270. The battery is still 12 volts, so you can still use 12. Right. What is the current flowing through? Now, because they are, well, let's label them. Let's call this R1, R2, R3. Because they are parallel, though, we know the currents add up to the total, but what we do know about parallel is that, what we also know about parallel is that the voltages are the same. So, and since they're also parallel to the battery, it must be the same as the battery. So V1 equals V2 equals V3 is also equal to V total, which is 12. Okay. So if you want to find individual currents, like in part B, then you would have to use, so it says find the current through the 88. So let's see, let's find V1, oh sorry, I1. I1 must equal V1 divided by R1. So when you find individual values, use the individual resistances. Unless of course, unless of course the total current goes through that resistor. All right, and we'll do one more, mastering physics number 16. All right, is this the one you wanted, Chris? Is this did you finish this one up? I don't know if Chris is still here. Number 16. Number 16 says a 12-volt battery is connected to terminals A and B in the circuit. Suppose that resistor R is 87. Oh, look, it looks exactly like today's problem. So instead, they're not drawing the battery though, they're just putting the resistors together. So we have a resistor, and then they combine and go back to B. So we're trying to find the resistance between A and B. All right. It says a battery is connected to A and B. So if I connected this to a battery, it looks exactly like today's circuit. This is 12 volts. All right. R is 87. Oh, this one here is 87. Now your values might be different. So on mine it says this one here is 87, the top one is 75, and the one in the front is 24. Okay. Part A says find the current in the 24. So the first one, part A, says find the current. So if I draw the current flow diagram, you'll see that it comes out of the battery and all of it goes through the first resistor. This is resistor 1. And so we could say that the current that goes through resistor 1, I1, is equal to the total current, I total. And once that happens, it splits up into two parts. Some of it goes through the first part here, some of it goes through the second one here, etc., etc. But similar to what we did today, let's go and combine this stuff to find the total resistance, right? REQ, we could do it in two pieces, or you could identify which ones are parallel and which ones are series, right? We know that the 75 and the 87 are parallel. These two here are parallel because they split and then recombine again. So let's label R2, R3. We can say that R2 is parallel, here's the parallel symbol, to R3. So R2 and 3 are parallel. But once they are parallel, they combine and are in series with R1. Okay, so if you take a look at the first example we did today, that's essentially what we did. We found the parallel component, the R23, which was 2, and then we added them up because now they are in series with the one in the front, right? So let's go back. So once we find the parallel, we'll add it up to the one in the front. Okay, so that means this is 24 plus the parallel of 2 and 3. The parallel of 2 and 3, you can use the parallel rule or product over sum because it's 2. 1 over 75 plus 1 over 87. Okay. All right, so let's see. If I did product over sum, that gives me the parallel times 87 over 75 plus 87. What is 150, 162. Plus the one in the front. The one in the front is 24. So that's 64.277777. If I use 2 sig figs, it's basically 64 ohms. And once you find the total resistance, you can find the total current. I total is equal to V total over rec. So that's 12 volts over the total 64 ohms. 12 over 64, 1.18. And then let's round this to 2 sig figs because our numbers are 2 sig figs. And that's 0.19 amps. Okay. Then it says find the current through the 75. So I want to find I2. So what is I2 equal to? Similar to what we did with the first problem today. If I make a quick chart, oops. I1, I2, I3, V1, V2, V3. Okay, I1 is 0.19, the total current. Okay, we can find V1. It's just R1 times I1. So 24 times 0.19 is 4.56. Now, of course, there is another way called the current splitter rule, but I'm not ready to teach you the current splitter rule yet. So we'll do it the long way for now. And then later on I'll show you the shortcuts, because if you learn too many steps it might be difficult, and then you start using parts of one method with the parts of another and you get lost, neither the sea nor the sand. So we'll take it in small steps. So I multiplied the two numbers, 24 and 0.19, to get the voltage 4.56. So that means we are losing 4.56 volts here, but we started with 12. So what's left over? What's left over must be 12 minus the 4.56, which is 12. 7.44 is left over. Okay, so V2 is 7.44, the leftover voltage. Then I2 must be V2 over R2, and that's 7.44 divided by 75. Divided by 75. 0.099 amps. Alright, so that's how you do 16 Christopher Tran, or Christian Tran. Whoops. So that's it for our review. We'll do some more tomorrow. Thanks for tuning in. I'll see you next time. Bye bye.